Hello and thank you for watching my video. My name is Astrid Krasniqi. I'm CCNA and CCNP certified instructor. Today we are going to cover CCNA Semester 3, Scaling Network, Chapter 5, Adjust and Troubleshoot a Single Area OSPF. Objectives for this chapter are Advanced Single Area OSPF implementation. It's advanced because for basic single area OSPF implementation you have covered on CCNA Semester 2, Chapter 8. Here we're gonna talk about modifying the OSPF interface priority to influence the DR and BDR election. Then we will configure a router to propagate a default route in an OSPF network. We configure OSPF authentication to ensure secure routing updates. And we should be able to explain the process and tools used to troubleshoot a single area OSPF network. Then we move on to section 5.2. Troubleshooting single area OSPF implementation. Here we will troubleshoot the missing route entries in a single area OSPF routing table version 2 and version 3 OSPF version 3 routing table. Okay, let's get started. 5.1 Advanced Single Area OSPF. Routing versus switching. A scalable network requires hierarchical network design. Scalable networks also require optimal reachability between sites. Remote network reachability is provided by routers and layer 3 switches, which operate in the distribution and core layer. Routers and layer 3 switches learn about remote networks in one of the two ways. First, remote networks are manually entered into the routing table using static routes. So you as an administrator, you go and type the static routes. But this is not very scalable. Imagine you're going to be writing static routes for the whole internet network, so not scalable at all. Or we can do it dynamically, which we implement routing protocols to learn the routes. So remote routes are automatically learned using dynamic routing protocols, such as Enhanced Interior Gateway Routing Protocol, EIGRP, or OSPF, Open Shortest Path First. Both of them, either what you use manual or dynamically, they have the advantages and disadvantages. Static routing, for example, have a look at this network. We have router 1 is connected to three networks. It's got one LAN on this side, 192.168.10.0/24, and this side the 11, another local area network, 192.168.11.0/24. Router 1 has got serial connection with router 2, 209.165.200.224.30. And router 2 has got 4 connections. One LAN 10.110/24, another LAN 10.120/24 has got a connection towards the internet, and it's got a connection towards the router 1. Now pretty much we're going to use this network to configure. If you do static routing, it says router 2 is connected to other networks and to the internet, and it's also my only way out of here. I just need a default route to reach any network that I do not know about. So for example, router 1, you don't really need to tell router 1 how to get to directly connected network. You don't need to tell how to get to this network because it's directly connected, or this, or this. But for these networks, yes you do. Now, because its only way out is router 2, router 1 will need only a static default route, all zeros. So for example, all our home routers, they have the same static default route towards ISP. Router 2 on the other hand will have a connection towards the internet. It's got routes there, but router 1 only has 2 networks that I need to know about. So I'm create 2 static routes. So router 2 can create 2 static routes only to reach this network and reach this network. So a network administrator can manually configure static routes to reach a specific network. Unlike a dynamic routing protocol, static routes are not automatically updated and must be manually reconfigured anytime the network topology changes. A static route does not change until the administrator manually reconfigures it. So static route has 3 primary uses. Provide ease of routing table maintenance in smaller networks that are not needed or are not expected to grow significantly. So for example, you have your routing table in a small network, you can configure it, a static routing, it's not going to grow that network, you can maintain it. If it does start growing rapidly, then you will not be able to maintain it because it will be very challenging. Routing to and from stub network. A stub network is a network accessed by a single route, and the router has only one neighbor. For example, a router 1 is a stub network. It's got only a single route to network 192.168.10 and another route towards 192.168.11. So router 2 can create two static routes to those two networks. Using a single default route to represent the path to any network that does not have a more specific match with other route in the routing table. Default routes are used to send traffic to any destination beyond the next upstream router. For example, a router, when he gets a packet, is going to look at that destination. Where is it going? Where that packet is going. And if he doesn't find more specific route on the table, then he was going to match the default route. Default route is all zeros. Any network is going to send it towards the default route. Dynamic routing protocol. It's a bit more. It's like if the only problem with dynamic routing protocol is that it's going to require more resources. A static routing, you can implement it on any router because it's not going to use any resources like CPU or RAM, while dynamic routing is going to use those resources. So static routing is considered more secure than dynamic routing because static routing is not going to share the information. Dynamic routing is very chatty, but we can make dynamic routing secure because we can implement authentication. Here the two routers are doing the same thing, but they are just exchanging the updates with the OSPF. Advantage of dynamic routing because is if one of the networks fails, then dynamically router 1 will inform router 2, and router 2 will update his routing table. That's a disadvantage with manual static routing because if this network fails, you have to literally manually go to router 2 and update the routing table. You don't need to do anything in router 1 because router 1 is directly connected. So a routing protocol allows routers to dynamically share information about remote networks. Routers receiving the updates automatically add this information to their own routing table. The routing protocol then determines the best path or route to each network. A primary benefit of the dynamic routing protocol is that the routers exchange routing information when there is topology change. This exchange allows routers to automatically learn about new networks and also to find alternative paths when there is link failure to the current network. So for example, from A to Z, you can have 3 or 4 paths. The routers will find out what is the best path to get to the Z. If towards A fails, then I'll recalculate and I'll find another path. I go towards B, towards route B. We'll see a bit later. Compared to static routing, dynamic routing protocols require less administrative overhead because once you configure dynamic routing, you can forget about it. Well, kind of. However, the expense of using dynamic routing protocol is dedicating part of the router resources for protocol operation, including CPU time and network link bandwidth. Open shortest path first. OSPF is commonly implemented link state routing protocol. Remember, we had two types of protocols. We had link state protocol and we had distance vector. Link state, they will keep in the memory the whole topology, like A to Z, right? And distance vector was just keeping like whatever the neighbor is telling. So it didn't know, like it just knew the distance, how far it is, and vector, what direction to go. So OSPF was developed to replace a distance vector protocol like RIP. However, OSPF has significant advantages over RIP in that it offers faster convergence and scales to much larger network implementation. So the features of OSPF are, it's classless. It is classless because it will send, it supports VLSM, so it does support subnetting and CIDR, classless inter-domain routing. It does support this because it does send a subnet mask with the updates. Efficient. Routing changes triggers routing updates, no periodic updates. It uses the shortest path algorithm to choose the best path. Classless, for example, there's not a big advantage to RIP version 2, for example, classless, because RIP version 2 does send updates, subnet updates as well, subnet mask. It's efficient because RIP version 2, for example, if you compare OSPF to RIP version 2 will send an update every 30 seconds. Now, OSPF doesn't. OSPF will do a triggered update. Only when something changes, it will send an update. it has this algorithm that is going to run the best path. It was going to choose the best path. So if it finds that, okay, well, I can go through path A or through path B to the destination, I'll run the algorithm to find the best path. Fast convergence. It quickly propagates network changes. When there's an update, the OSPF routers will send a link state advertisement. And as soon as they send the link state advertisement, all the neighbors will just flood that link state advertisement to every router, right? So that makes a very fast convergence. We talk about link state advertisement a bit soon, very soon. Scalable. It works well in a small and large network sizes. Routers can be grouped into areas to support the hierarchical system. And it's secure. It does support message digest 5 or MD5 authentication. When enabled, OSPF routers only accept encrypted routing updates from peer with the same pre-shared password. So security is there. To configure a single area OSPF, we're going to use this network. I'm sorry, I said the other network first, but we're going to use this network. So I don't know, you can like pause the screen, pause the video, draw it on a piece of paper as you're learning, but this is the network. Okay. So first thing you need to do when you configure in the OSPF, you need to enable the OSPF. So you have to go to the global configuration mode. So you are in global configuration mode and you type router. Then you can choose what protocol, dynamic routing protocol you want to use. In this instance, we're using OSPF. And then we have the type of process ID. This process ID is locally significant only. We can pick any number that we want. The neighbors, they don't have to match. Now, you can use anything between 1 and 65,535. Usually, most of the people will just use 1, but you can pick any number that you want. Now, the neighbors, they don't have to match this. It's a bit different to the EIGRP, for example. So, okay, like I said, locally significant do not have to match others, OSPF routers. It differs from EIGRP. We are using the same process ID simply for consistency. So, for example, here is just a process ID. Yeah. So if I look at the my task manager, I can see the different process ID. It doesn't have to be the same with the neighbors, the process ID. A router is known to OSPF by OSPF router ID number. So all the OSPF routers, they have to have a router ID. If they don't have a router ID, they will not be able to speak OSPF. It's like the name, yeah. If they don't have, no OSPF. There's few ways that we can get that router ID. So link state database uses OSPF router ID to differentiate one router from the next. You have to make sure that within the area, the router ID is different. Each router has a unique router ID. Because if you do have you can have same router ID everywhere, but it's going to cause a lot of problems. So the way we get it, by default, the router ID is the highest IP address on active interface at the moment of OSPF process startup. However, for stability reason, it is recommended that router ID command or loopback interface can be configured. Now, Cisco routers will derive the router ID based on 3 criteria on which of the following precedents. First, IP address configured with the OSPF router ID command. So it's the ID, yeah? No, it's not an IP address. But when you do OSPF router ID command, that will have the highest priority, or precedence, will win. So, for example, router ID command 1.1.1.1. It's like an IP format representation, but it's just a number. If you don't configure that, then the router will go and pick the highest IP address of any loopback interfaces. So it will go and find out, do I have any loopback interfaces anywhere? Give me the highest IP address. Now, it's important to know that that loopback address doesn't have to be part of the OSPF. It could be all not there, but they will pick it. If you don't have a loopback, then you have to have one IP address that's enabled. So it will pick the highest active IP address on the physical interfaces. Now, that as well, if that IP address is not part of the OSPF, it will still pick it. If you don't have that either, if you don't have any IP addresses that are all configured, nothing, no shutdown anywhere, then the OSPF will give you an error. It will say, okay, I can't start the OSPF. The interface does not need to be enabled for OSPF, i.e. it does not need to be included in the OSPF network command. So even though if it's not on the OSPF, it will still pick it because it's found the highest loopback address or highest IP address. But it will go through these. It will find out, have you configured router ID? No. Find out the loopback address. Do you have a loopback anywhere? Interface is configured? If yes, yeah, pick the highest. If no, then move to the third task, third step. Try to find out the highest IP address on the physical interfaces. So any unique arbitrary 32-bit value in the IP address format, dot decimal can be used. So it's not an IP address, it's IP address format. So anything you can use. Router ID 11111. Or I can use router ID 255.255.255.255. That's no problem. Because it's IP address format. So it doesn't really represent anything apart from it tells, okay, this is my router ID, or router 1 says this is my name, 1111. Now if the OSPF has already started, the router will tell you, okay, well, for this to take effect, you need to reload the router, shut down, switch it off and switch it back on, or clear IP OSPF process, right? Clear IP OSPF process to clear the process, start again, then it will take effect. So if this command is used on OSPF process that's already active, then the new router ID takes effect if you reload the router, or after manually restarting the OSPF process using the clear IP OSPF process privilege exec command. Now when we do clear IP OSPF process, the router tells you, are you sure? And it says no here. So if you just press enter, you don't type anything, press enter, it will take it as no. That's the default. But you have to type why. Because the reason why the router is being careful, asking you another question, are you sure you want to do this? Because everything, all the neighbors are going to go down, all the routes that you learned, they're going to go, and you're going to restart again everything. The other step to do, the way to do it is to enable one loopback interface. So interface loopback 0, IP address 1111, and give an address, and the router, if you haven't done a router ID, it will find out this loopback address and it will pick it as a router ID. The network command, same function as when used with other interior gateway routing protocol. Any interfaces on the router that match the network address is the network command will be enabled to send and receive OSPF packets. For example, this network or subnet will be included in OSPF routing updates. When we do OSPF, we do require the wildcard mask. So used to specify the interface or ranges of interfaces that will be enabled for OSPF. For example, this is the command network. So you are in the global routing configuration, and then you enter the specific routing protocol configuration. You type network, what network you want to advertise, the wildcard mask, and what area does it belong. The area ID refers to OSPF area, a group of routers that share this link state information. So for example, in the area, all the networks, all the routers, they will have the same database, and they will keep every link up to date. It's like A to Z, or that's the area. So we are covering this area. You have the A to Z, everything up to date. If the network goes down within the area, you will find out right away. Identical link state database. This is known as single area OSPF, right? So OSPF has to start with area 0. Area 0 is the backbone area as well. The network command must be configured within the same area ID on all routers. So for example, router OSPF 10, process 10, we do router ID 1111, make sure that we type router ID 1111. Then we type network 172.16.1.0, 0.0.0.255, area 0. So we enabling this network to be a part of the OSPF. Now, to derive to this wildcard mask, all you have to do is put 255s on the top, 255, 255, 255, 255, and subtract the subnet mask. So minus 255, 255, 2550. So when you do that, that will give you the area ID. Right. I don't want to take too much time here, but very quickly, if I can, show you how to get to that area ID. So let me just open the notepad here. how to get to wildcard mask. So for example, if your network is, like we say, /24, that means 24 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Then it's 32 bits the IPv4, so 1, 2, 3, 4, 5, 6, 7, 8. Right, if you convert this to decimal, it's 255.255.255.0. These are the three things. Yeah, same thing, the subnet mask. Now to get to the wildcard mask, if the network subnet mask is like this, all you have to do is type 255.255.255 on the top, and you minus your subnet mask. Whatever comes up, then that's your wildcard mask for that network. So 255 minus 255 is 0, 255 minus 255 is 0, 255 minus 255 is 0, and 255 minus 0 is 255. So that's it. If you have a, for example, /28, say you have /28. Now 28 up to there was 24-bit, 25, 26, 27, 28. So I'm going to write 1, 2, 3, 4. That's 28. It will be 255, 255, 255, 240, yeah? Because 128 plus 64, 192 plus 32, 224 plus 16, 240. So 255, 255, 255 minus 255, 255, 255 dot 240. So 255 minus 255, 0, 0, 0, 255 minus 240, it's 15. So that's, we got the subnet mask for that. Sorry, the wildcard mask. Okay, going back. Right. So I hope you got that. Now, network 172.16.1.0 with the wildcard mask, this we are advertising. At the moment, there's not going to be any neighbors because the updates are going to start going here. The hello messages are going to start flowing towards the gigabit interface. When you enable there 172.16.3.0 with the /30 the subnet mask, so the wildcard mask will be 0003 area 0. Now the updates, the hello messages, they're starting going this way as well. And then we say 192.168.10.4 for wildcard mask 0003 area 0. So the updates, all the hellos are starting going that way. That's it. We're done. There's not going to be any neighbors until we enable the in router 2 and router 3 as well. Optional method. So this is another method that we can identify OSPF networks, and this is actually preferred. We're moving towards this way. So no network, we don't have to type in the network command like we did before, yeah? So we don't have to, we still have to do this, router OSPF10, router ID 111 and whatever. But we don't have to type the network command, right? What we have to do is go to each individual interface. So interface G01 and say IP OSPF10 area 0. And then interface serial 000 IP OSPF10 area 0. So we identifying exactly the interfaces rather than just doing it with a network command. The same way we could have done it before with a network command, if we set 192.168.10, for example, 192.168.10.5 and all 0, 0, 0, 0, 0. Identify exactly the interface. Okay. Passive interface. So by default, OSPF messages are forwarded out of all OSPF enabled interfaces. So there's going to be hello messages going this way. And as you can see, there's no neighbors expected to be in there. So for that reason, we have to make that interface passive. So sending out unneeded messages on a LAN affects the network in three ways. First is an inefficient use of bandwidth. Second, inefficient use of resources. And the third, most risky, is a security risk, because some user can bring his laptop and enable OSPF in his laptop and become neighbors with you and get all your routes. Interfaces which do not connect to other OSPF neighbors should be rendered as passive. So what you have to do is go to the OSPF process and say passive interface, and the interface that should be passive. So in this case, gigabit Ethernet 00. Another way to do it is make everything passive, and this is preferred. So make everything passive and then say no passive interface serial 000, this one. So no passive means start sending updates or hellos, and no passive, so you just make everything default passive, and then no passive interface is the one that you want. This is good, because for some reason in future you create another loopback or so on, then you have to remember, oh okay, I'll have to go to the OSPF and do a no passive interface that loopback. No, make everything passive default and no passive, just the ones that you do want to enable for OSPF. To verify the OSPF, we do show IP OSPF neighbor command to verify the router has form adjacency with its neighbors. If the router ID or the neighboring router is not displayed, or if it's not in show as being in the state of full, the two routers have not formed the adjacency. So we say show IP OSPF neighbor. Here what we see is the list of the neighbors as they ordered the way they were learned. So we learned neighbor 3 first, and then the neighbor 2. Then we see the priority. Now this priority, if it's point to point, like a serial interface like we saw earlier, it's not really used at all. It's set to 0. It's only useful when we have a multi-access, if we connect those OSPF neighbors through the switch. Then we use this priority to elect the DR designated router or BDR, backup designated router. The state, what is the state? For the state of the OSPF enabled interface, the full will mean that the router and its neighbor have identical OSPF database. Now you will have in the serial or point to point, you will have a full. Sometimes on the multi-access, for example with a switch, there's going to be a two-way, right? So the routers will only make a full adjacency with a DR. If two routers are not DR or BDR, they're not going to make adjacency, so they're going to be on two-way. But you'll see that on when we do the multi-access. That time, the amount of time remaining before declaring the neighbor town, so 37 seconds left for router 3 and 30 seconds left for router 2. Now the hellos are every 10 seconds. The dead time is 4 times hello, right? And that's on the fast link. On the slow link is every 30 seconds, and dead time again times 4. So 40 seconds. So if I miss 4 hellos, for example, well, 3 hellos. If I miss them, then I'm going to declare, well, 4. I'm going to declare the neighbor down or dead. The address, where you hear in the address, the neighbor's IP address, for example, that's the addresses of the neighbors, and the interface where you're hearing these hellos, where you have created this adjacency, your interface, local interface. That's the neighbor's address, and that's your interface. Show IP protocols. This command will provide a quick way to verify a vital OSPF configuration information. This will include a process ID, what process we are running. Like we said earlier, this doesn't have to match. A lot of students, when they're troubleshooting, they see this different and they start worrying about this right away. No, this doesn't have to match. Router ID. Router ID has to be unique, right? So make sure that you have a unique router ID on all the routers. What routers what networks we are advertising. So what network command we have typed, and what are the neighbors. Plus we can see the distance, administrative distance. 110 is the default for OSPF. Show IP OSPF, this command is great. Show IP OSPF, for example, tells you a bit more information. What we see here is, again, same thing, OSPF process ID, but we can see what area we are. So we are in the backbone area, and what is our routers, how many neighbors we have in this router. To verify the OSPF settings, and this is a great command, show IP OSPF interface. Command provides a detailed list for every OSPF enabled interface, and is very useful to determine whether the network statements were correctly composed. So this is great as well. This is really good command. First it tells you what area you are, what type of network is it, so the network type has to match, what is the cost for this network or this interface, what is the hello time and dead time, right? And now this has to match. So hello time, if it's set to 10 seconds on this side, the neighbor has to set it to 10 seconds. So if it's set to 20 seconds on the other side, there's not going to be neighbors. So this has to match. And what is your neighbors? Show IP OSPF interface brief. This is briefly going to explain what interfaces are enabled for OSPF. For example, we have enabled 3 interfaces, all of them the process ID of 10, all of them on area 0, and this is the IP address, and including the cost. Here with this interface we're really finding out what is the cost. The cost for OSPF is used from bandwidth, derived from bandwidth. So we have a reference bandwidth in bits per second. Reference bandwidth is 1 billion, right? 1 billion divided by default bandwidth in bits per second. So for example, 1 billion divided by 10 billion, it's under, yeah? So we just set it to 1. 1 billion divided by 1 billion, it's 1. 1 billion divided by 100 million is 10. So gigabit here, it means that we have changed it actually, because all these three by default is 100 million. So all these three is going to be equal to 1. We have to see later on, we see how we change that as well. So gigabit interface is 1. The serial 00 is 647, and serial 001 is 15,625. Okay, configuring single area OSPF version 3. Very quickly here. The following is a review of basic implementation of version 3 routing protocol. The example displaying the topology used for configuring OSPF version 3. The routers in the topology have a starting configuration including enabled interfaces IPv6 addresses. So everything is being configured correctly. We have IPv6. Make sure you don't make mistakes on the letters and numbers and so on. There is currently no static routing or dynamic routing configured. So we do show IPv6 interface brief. We can see that we have configured. We didn't configure link local. We have configured the unicast, global unicast address. All interfaces on router 1, 2, and 3 except the loopback on R2 are within the OSPF backbone area. So first thing we have to do, enable IPv6 unicast routing. Then we have to enable the process IPv6 router OSPF 10. Now it will say to you process OSPF version 3 cannot be picked up a router ID, because router ID it will pick up a version 4 IPv4 format. So we have to, it says here, please configure it manually. So okay, fine. We say router ID 1111, and we change the reference bandwidth to 1000. So reference bandwidth is changed. Please ensure reference bandwidth is consistent across all routers. And you can see that version 3, OSPF version 3, it says config RTR. Version 2 was saying config -router. Verifying router ID. Clear IPv6 OSPF process. Now we resetting everything. Again, it's saying you sure? Say yes. And we should show IPv6 protocol, and we should see that we have the new router ID. Next, the interface participating in OSPF are configured. So we have to go same on each interface and enable the OSPF on that particular interface. The gigabit Ethernet 00 is also configured to reflect its true bandwidth. Notice how there is no wildcard mask required when configuring OSPF. So for example, now we are setting the link local addresses as well. Yeah, so we go to G00 IPv6 address FE880::1. We're saying link. This is link local address, and we're saying IPv6 OSPF 10 area 0. It's good to know to have this link local address configured, because all the updates they're gonna have this link local as a source. We go to the interface serial 00, we enable that, and in 001 as well. You see, all link local addresses are exactly the same. F8E::1, FE80::1. The reason is because these are confined within the network. They do not travel from one network to another. So you can have the same IP address. It's similar to APIPA in version 4. Okay, we have enabled the bandwidth 64 as well to reflect the bandwidth for serial 001. To verify it, show IPv6 OSPF neighbor command to verify the router has formed an adjacency with its neighboring routers. If the router ID of the neighboring router is not displayed, again, if it's not there, we don't have a neighbor. And the state, what is the state? It's exactly the same, well, not the same, but similar to version 2. By the way, I need to tell you that in version 3 as well, you can configure IPv4 as well. This will enable IPv4. You can have IPv4 and IPv6 on version 3 using something called address families, which is your CCNP studies. Show IPv6 protocol. Command provides a quick way to verify vital OSPF configuration. So for example, we see what is the router ID, what interfaces are enabled for OSPF, what is the process ID, show IPv6 route to OSPF. Command provides a specific about OSPF routes. Okay, this is not the it's not the display. Show interface serial 00. We can see here the bandwidth. The routing table will be different. Yeah, there we come. Show IPv6 route OSPF. Now we can see what we have learned. We have learned about this network via, I told you, link local, the neighbor. That's going to be the source for each update. Show IPv6 OSPF interface brief. Command is useful to display the summary and status OSPF version 3 enabled interfaces. Okay, that's it. Thank you for watching my video. Now, if you would like to see the configuring basic single area OSPF version 2, please follow the link. Thank you for watching my video, and bye bye.